All right, let's see if I can make this last video for respiratory system make sense. So let me see if I can do it fast. I left you with Dalton's Law, and I've done a lot of scribbling since I switched from the last video, so this is kind of a mess. Here's what I want you to focus on. This is Dalton's Law. Don't write that down. Please don't write that down. I want to explain what this all means. What did he say? If you think about the atmosphere, our atmosphere, the atmosphere on Mars, the moon, wherever you happen to go, it's not just one gas that's in this atmosphere. There's multiple. Right now in our lab, there's CO2, there's nitrogen, there's O2, there's a number of different gases that I'm inhaling and exhaling at all times. Each one of those gases has its own what is called partial pressure. So essentially, how much is there? How much pressure is there? How much does it want to move across a membrane? And what Dalton came up with was this idea. He said the partial pressure of, for example, O2 has no impact. It's completely independent of the pressure of CO2 or the pressure of, I could have done PN2 for nitrogen. He said they're all independent. They're all completely independent. This allows us to understand how gas exchange actually happens in those alveoli between the opening and the circulatory system, those capillaries. So let me clean that up a bit. Now, what we find is physicists will tell us partial pressure at sea level of O2 is about 159, 160. I believe it's milligrams of mercury. I can check on that, doesn't matter. We just need relative numbers. Partial pressure of CO2 right here at SC4 in St. Clair County is about 40. Well, we have to start somewhere on this. What I've done is I've tried to put together a closed loop of our circulatory system. And so let me start somewhere. When we return back to the lungs, our partial pressure of O2 is somewhere around 40, and CO2 is somewhere around 45. Now that one little data point right here it's not really that important until we look at everything in perspective. So let's look at what's going to happen as I go in a clockwise direction. As I get to the lungs, and we're ready to do gas exchange between those type 1 alveolar cells and the capillaries. If PO2 is 159 and PO2 is 140, what's going to happen is this. O2 will, not magically, but through the laws of physics, jump back into the blood. Partial pressure of CO2 is 45. And here it's 40. So CO2 is going to jump out of the blood. So we have that gas exchange based on physics and physics alone. Now, as we keep going to the right, let me make sure I've got my numbers at least close. Okay, PO2 is then increased to roughly 100. And partial pressure of CO2 is dropped to roughly 40 because it's left, it's gone into the lungs, and you've exhaled, you've constricted and contracted the pleural cavity, and you've exhaled. Now look at what happens once we get down to the rest of the body. Well, if my partial pressure of O2 is 100, and partial pressure of O2 in the tissues is relatively 40, O2 is going to leave. And think about this for a minute. Vigorously exercised cells, when I ride home in a little bit, I'm going to be using the big muscles of my legs. I'm not going to be using the muscles of my arms that much. So how does the O2 know to jump into my legs and not into my arms? Well, it's all about this differential. If I'm using a lot of O2, this goes down further and further and further and further. So those tissues are going to have O2 jump out into them. On the other hand, partial pressure of CO2, my waste gas is going to go up in those vigorously exercised and used cells. Therefore, the CO2 wants to jump into the circulatory system. We come back around, CO2 jumps out, O2 jumps in. Collect more CO2, drop off more O2, and we come back and do the exchange in the lungs. So where we started on video number 1 was me telling you that my parents told me a long time ago that I exhale CO2 and I inhale O2, and I just believed them. I didn't know physics when I was 5. This is why. This is gas exchange. So we've talked about inhalation and exhalation. We've talked about partial pressures. We've talked about moistening and warming the gases as they come through. Now we're talking partial pressures. This is it. Now, last thing that I want to mention, I might do an addendum to this later on, maybe. When we talk about COVID-19, how is it different than pneumonia? Because I'm hearing people on TV and on the radio going, oh, COVID-19 is just like the common cold. Yeah, the cold is also a coronavirus, but there are dozens of coronaviruses and they're not all the same. Essentially what the virus that causes COVID-19 will do is, and how it differs from pneumonia, is if I go back to this slide, let me go back to this. When we talk about just general run-of-the-mill pneumonia, which nobody who's ever had pneumonia would think is general or run-of-the-mill, pneumonia will attack parts and make it difficult to breathe and possibly kill you. What coronavirus or COVID-19 will do is attack essentially all of the lung. So it's not specific, it's not particular. It doesn't say, well, I just want to attack one part in one area, which is why it essentially moves into the world of pneumonia and could kill you. So, with that being said, wash your hands, don't relax, don't sit back and think, okay, this whole thing is done. It's not. We're gonna ride it out for a while. I have a faculty member that I know a couple of doors down here who has a neighbor on a ventilator. I think I mentioned before, possibly I know of at least 2 SC4 students that have COVID-19. So be careful and don't relax. Don't put your feet up for a while. So with that being said, on that really uplifting note, I'll get these online as quickly as possible, and I'm going to push out an email to everybody that will let you know that this exciting email series is online, and I will be in contact soon.